To understand cross-multiplication, let us again write the general form for the pair of linear equations in two variables. Please recall that, if we have to solve, let us say, eliminating y, we can either do that by dividing the equations by coefficients of y, or by multiplying each of the equations with coefficients of y from the other equation. In both the cases, with the resulting new pair of equations, on solving by eliminating y, we will get the values of x as x equals b1 c2 minus b2 c1 by a1 b2 minus a2 b1. By substituting this value of x in either of these equations, we will get the value of y as y equals c1 a2 minus c2 a1 by a1 b2 minus a2 b1. If we look at the result carefully, the denominator is common for both x and y, hence, we can summarize the result as x by b1 c2 minus b2 c1 is equal to y by c1 a2 minus c2 a1 is equal to 1 by a1 b2 minus a2 b1. In cross multiplication, we can simply skip the intermediate steps of elimination and substitution, to directly have the values of the two variables from the coefficients itself. The only challenge here with this direct method is to remember and recall the solution equation correctly. Let us see how to fix the equation in our minds. Imagine A, B, and C in clockwise order in a circle. Adjacent to each, write the corresponding coefficients with suffixes from pair of equations as shown. Write x opposite to A, y opposite to B and 1 opposite to C. Here, we will notice, as we move from B to C, we have x, as we move from C to A, we have y, and finally, as we move from A to B, we have 1. Now, the only thing to remember is, as we pass by x, y and 1, we have to cross-multiply and subtract, only in the clockwise direction. Hence, we can obtain from this figure, the solution equation, x by b1 c2 minus b2 c1, is equal to y by c1 a2 minus c2 a1, is equal to 1 by a1 b2 minus a2 b1. Therefore, we can always make this a rough figure, to recall the expression, without actually memorizing it by heart. Here, it is worthwhile to note, that when a1 b2 minus a2 b1 is not equal to 0, we will have a unique solution. When a1 b2 minus a2 b1 is 0, we can either have no solution, or infinitely many solutions depending upon the value of c1 by c2 with respect to the values of a1 by a2, and b1 by b2. These are the exact same rules that we have already covered earlier. Let us see a few examples where we solve the pair of linear equations by cross-multiplication method. Let us see the following example in which we try to understand the application of algebraic cross-multiplication. From a bus stand in Bangalore, if we buy 2 tickets to Malleshwaram and 3 tickets to Yeshwantpur, the total cost is 46 rupees. But if we buy 3 tickets to Malleshwaram and 5 tickets to Yeshwantpur, the total cost is 74 rupees. Find the fares from the bus stand to Malleshwaram and to Yeshwantpur. Let cost of each ticket, Bangalore to Malleshwaram be rupee X and Bangalore to Yeshwantpur be rupee Y. As for the first condition given, 2 times x plus 3 times y equals 46. As per the second condition given here, 3 times x plus 5 times y equals 74. We will now rewrite both the equations in the format, a times x plus b times y plus c equals to 0. We can now compare the coefficients, a1, a2, b1, b2, c1, c2 with the values given in the given conditions. Now, we are ready to apply the algebraic cross-multiplication method. Substituting the values of the coefficients on comparing with the standard form, we get the following algebraic equation by cross-multiplication. On simplifying the equation, and separating the two equations from the common equation, we get the values of x and y as rupees 8 and rupees 10 respectively. Now, let us consider a second example, for which values of p does the pair of equations given below has a unique solution. Let us now see the solution. Comparing with the standard form of equations, that is, a times x plus b times y plus c equals 0, we get the value of the coefficients a1, a2, b1, b2, c1 and c2. Now, we are ready to apply the algebraic cross-multiplication method. Substituting the values, we get the following equation. On simplifying, we get the following equation. Now, for the given pair of equations, the condition for them to have a unique solution is a1 times b2 minus p1 times a2 is not equal to 0. In our case, this corresponds to 8 minus 2p is not equal to 0. From this condition, we get p not equal to 4. Thus, we can say that the given pair of linear equations will have a unique solution if p takes any value other than 4. Now, let us see another example. For which values of k does the pair of equations given below have infinitely many solutions? Let us now see the solution. Comparing with the standard form of equations, that is, a times x plus p times y plus c equals 0, we get the value of the coefficients a1, a2, b1, b2, c1 and c2. Now, for the given pair of equations, the condition for them to have infinitely many solutions is a1 by a2 equals p1 by b2 equals c1 by c2. In our case, this corresponds to k by 12 equals 3 by k equals minus of k minus 3 by minus of k. From this equation, we derive two quadratic equations in k. From the first quadratic equation, we get the values of k as 6 and minus 6. From the second quadratic equation, we get the values of k as 0 and 6. From the three values obtained, we find that the value of 6 satisfies both the quadratic equations. Thus, we can say that the given pair of linear equations will have infinitely many solutions if k is 6.